morning, everyone. Uh, in this work, the flexoelectric characterization in different strain and kinds were proposed using a Kelvin probe. About the flexoelectricity, uh, important works have been carried out by our research group exploring the flexoelectricity in addition to devices based on this effect. Um, Flexoelectricity is a property of a dielectric material whereby it exhibits spontaneous electrical polarization induced by a strain gradient. Flexoelectricity is closely related to piezoelectricity, but while piezoelectricity refers to polarization due to uniform strain, flexoelectricity refers specifically to polarization due to strain that changes from point to point in the material. Different from triboelectricity, flexoelectricity does not require contact or friction with other surfaces. Similar to piezoelectric effects, uh, charge buildup is a spontaneous outcome of elastic deformation in dielectrics, but is allowed by symmetry in any material. This electromechanical response to strain plays an important role in robotics and sustainable energy harvest device, sensors, actuators, and transducers. In general, flexoelectric measurements are performed directly on the material or via induction electrodes. Here, we propose the flexoelectric characterization in different strain kinds through the Kelvin probe. The Kelvin probe is a high resolution and precision vibration capacitive electrode used for measurement of potential and surface electric charge without contacting the sample. In this figure can be seen a typical feedback circuit of Kelvin probe. About the experiment setup, a linear ball screw actuator connected to a DC stepping motor and controlled by a microcontroller board was used to perform a tensile, compressive, and flexural tests. The electrostatic potential measurement during mechanical tests were made with a non-contact Kelvin probe attached to a mechanical arm capable of moving horizontally, kept 2 millimeters above the testing material. Um, Rubbers undergo large elastic deformations at low stress, but recovering its initial shape after the stress is removed. The stressed natural latex presents high electromechanical conflict, but on a few studios deal with the electricity of high deformed elastomers. The electrostatic mappings are timely. Natural latex tube Following extension display non-homogeneous charge distribution. In fact, charge separation is expected on rubber subjected to elastic strain, but this is not observed when using commonly reported techniques for flexoelectric characterization. Um, Continuous stretching has higher electrostatic potential gradient compared to stretching after relaxation. Um, about the compressive and flexural results, electromechanical effects were also measured in silicon rubber under compressive loads. Mechanical compressions induce sharp positive potential peaks, uh, um, where a fast change in charge is followed by a slow electrostatic potential decay. When the compression load is removed, sharp negative potentials uh, are displayed on rubber, but decaying toward to close to zero equilibrium potential. PT samples were subjected to flexural loads. Uh, when the PT sample is fully folded, a positive potential with the measurement measurement error. So this electrostatic potential uh, was observed at ITRES for all specimens tested in our apparatus. Uh, Moreover, PT undergoes an important physical transformation upon bending, creating a rich and opaque color in the photo regions. So the electric response of dielectric materials subjected to different strain stimulus was measured with non-contacting Kelvin probes. Uh, Many important features of electromechanical coupling that could not be observed with standard techniques current used to characterize the flexoelectric effect were easily revealed with electrostatic methods. So, thus, the electrostatic Kelvin method presents a robust and effective alternative protocol for flexoelectric characterization, making possible non-contact and non-destructive real-time monitoring of electromechanical couplings in dielectrics. Um, thanks. Thanks for your attention.